All right, so for this demonstration slash lab, we're going to be looking at a electric or electron charge to mass ratio apparatus, or EM apparatus. So the idea is we got the following. We got a coil right here that's creating a relatively uniform magnetic field pointing either this way or this way. We'll ultimately be able to determine it based on how these electrons are cycling around. That green circle you see is a bunch of electrons that are being shot off some metal, and we can see them because as they fly through the rarefied gas that's in there, which just means a low density gas, they're bouncing off the gas molecules, and that causes light to be emitted. So in order to get those things to be launched out, we got a couple things going on. We got a power supply that's hooked up to a tiny little heater, so you can see the part right there where it's kind of slightly bright and orange. There's a little hot piece of metal there that's just being heated up. Then near that hot piece of metal, there's two little electrodes, two plates around it, and then a big voltage of, how much are we putting out? Only about 50 right now. Can actually crank that up. And so that voltage ends up determining sort of how strongly those electrons are being pulled off of the metal. So here you can see, if I put that in focus, depending on how strongly the output or that voltage is tearing the electrons off, determines how big the radius of the circle is, or it helps determine it. Again, the whole point of heating is that when we heat up the metal, it makes it much easier for this applied potential to tear the electrons off and launch them around in the circle. And then finally, the other one here is, of course, just controlling. This here is running the current that goes to these Helmholtz coils. Helmholtz coils are just a configuration of two coils that makes a relatively uniform magnetic field in a region. So we got those Helmholtz coils. With current going through them, we can adjust that current as well. Stronger the current, the stronger the magnetic field, and that would, because it's a stronger field acting to make the things go in a loop, that's why increasing the current, increasing the magnetic field, decreases the radius of this. And so it turns out that based on our knowledge of the conditions for going in uniform circular motion, and that was a nice circle. So we have a formula for the centripetal force necessary for that to happen. Plus, we know the strength of the magnetic field that acts on something. We have a way of being able to relate the observed radius of this, the observed voltage that we're putting in to make it run, the known strength of the magnetic field, which we can determine from the coils, and a bunch of pieces come together, and then based on the particles that are flying through here, in this case the electrons, it turns out we can solve for the ratio of the electric and magnetic field, the ratio of the electron's charge to its mass just based on observable stuff. If we want to independently know the mass or the amount of charge, then we would have to do additional experiments, but this gives us a way of being able to know the ratio between those things just based on stuff that we can measure. There's one little side thing. I can hold this and move around. Oops, pressing buttons on my phone. Right now, here we can see that while this is moving in a relatively circular path, because the direction that the electrons are launched is overall perpendicular to the field, I can come in with a nice powerful magnet and change the amount of magnetic field in a region. So here, by bringing a big magnet in, you can see that I'm able to now cause the electrons to spiral off in some direction. They're already kind of spiraling because this thing isn't exactly lined up as it should be. I'm out of focus now. But yeah, gonna fix. Camera isn't really going to work well in the dark. Get a little closer. And so depending on the relative direction of the magnetic field overall and the direction that the particles are initially launched at, will overall determine how they behave in the field. And that's the thing we observe with charged particles moving through a magnetic field. Depending on their initial direction, if they're exactly perpendicular to the field, they'll just run around in circles. And if they're not, then the part of their motion will be to run around in a circle, but the components of their velocity that are not perpendicular to the direction of the field will cause them to go off in some direction, and giving us the spiraling that we saw there. So as far as lab-related stuff associated with this would go, we'll give some data associated with varying some of these quantities, and you're going to use the data that's available to calculate, what the ratio, or to verify that we can calculate the ratio of the charge of the electron to the mass of the electron.